Okay, if we didn't remember our exponent rules from our review earlier, let's go over some of them. I'm just going to scoot this to the side for a second. If you have two x values that maybe you're multiplying together, x to the third times x to the fifth, what do you do with those two exponents? You add them. So you're saying if I am multiplying, I add. Okay, cool. If you have two exponents like x to the fifth and it's divided by x to the third, what do you do with those? Subtract. So you're saying I divide, I subtract. Okay. If you have an exponent raised to another exponent, what do? Multiply. So you have a power to a power, you multiply. These are our mad spam rules. The rest of the rules also exist. So anything to 0 power is 1. The negative exponent goes to the bottom. All of those things still exist. However, we have these mad spam rules that you probably learned about in Algebra 2. Do you remember this acronym? Okay. Mad spam tells us if we multiply, we add. If we divide, we subtract. If we have a power raised to a power, we multiply the exponents. Cool. Those exponent rules pretty much still apply when it comes to logarithms. Because logarithms and exponentials are inverses of each other, a lot of the rules stay the same. So if we look at these properties of logarithms, not properties of exponents anymore, we have the exact same rules. What am I doing when I add together two logarithms? What was it a second ago? What went with add? Multiply. So multiply still goes with add. If you are adding two logarithms together, you can condense it by multiplying the arguments together. So for example, if we had log base 2 of 5 plus log base 2 of x, the bases have to match, by the way, same as the exponent rules. All we do is take the 5 and the x and we multiply them together. So it's log base 2 of 5x. Now this rule works both ways, where we can also expand it. If you started with something multiplied inside one logarithm, you can expand it to two logarithms by taking them apart. The quotient property is still the same. A second ago when we had subtraction, what were we doing with those two things? Dividing them. So divide, subtract still exists here. Same like exponent rules. If you are dividing things inside one logarithm, you can split it apart into two with subtraction, or vice versa. If you're subtracting two logarithms with the same base, you can divide their exponents. Basically, the thing that's negative goes in the denominator. Oh, that sounds familiar. The thing that was negative went to the denominator. So if you look at this example here, let's say we have log base 3 of y divided by 4. I can expand that by saying log base 3 of y minus log base 3 of 4. Do we follow? Okay. The last rule that we had for exponents that we went over was power to a power means multiply. Now this still exists, but it looks a little different for logarithms. We have our argument raised to a power. So what we are going to do is we're going to loop that to the front, and we're going to multiply it in front of the logarithm. Notice that the n moved to the front, and vice versa. If you have a number in front of a logarithm, you can take it up to be an exponent of your argument. So for example, we have log base 7 of 3 raised to the x power. So we're going to take that x and we're going to move it to the front of the logarithm. So now it is x times log base 7 of 3. Now what's really cool about all of these rules is that it actually allows me to take complicated logarithms and write them with different transformations. So I can take horizontal transformations and make them vertical, and I can take vertical transformations and make them horizontal. That's all outside, inside sorts of things. So in the three examples we had here, we started with a horizontal transformation. This is a dilation by 1/5. But once I use the exponent property, this is just a constant. Log base 2 of 5 is something we could type in our calculator. It'd be some ugly decimal. But that's a constant. It's not going to change. There's no x value in this logarithm. So we have created a k plus a log of x. That is a vertical translation up or down k units. For the other one, for my divide subtract, I started out with a horizontal dilation of 4. You use the reciprocal. And once I use the exponent rules, I get that this is a constant. There's no variables here at all. This is just a plain number. It's an ugly number. It's like, a decimal. We'd have to use our calculator to find it. But again, we just ended up with our logarithm plus some value k. Minus some value k. So that's a vertical translation down. In this example here, it's kind of weird because this is an exponential, so I'm going to write a new example to make my point across. We're just going to switch these. Let's say I had log base 7 of x to the third power. That 3 would come out to the front, so we would have 3 times log base 7 of x. I have now created some k value in the front, which, if we remember, numbers multiplied in front of a function is a vertical dilation. So all of these transformations, all of these manipulations of the logarithm are going to allow me to see transformations in two ways, either a horizontal transformation when it's inside the parentheses, or a vertical translation when it's outside the parentheses. But we'll get to the transformations in a little bit. Let's talk about just the exponent rules themselves. Let's work on just using, I said exponent rules, I meant logarithm rules. Let's condense these logarithms into one. So we just have to use the mad spam rules here. Thing I want you to identify is what's happening to the two logarithms. So what am I doing here? Adding. Adding changes to what? Multiplying. So the way I would write this would be log base 4 of, and then I use parentheses to say we are doing x times y. Now in math, we don't write the times symbol anymore, but because these are your notes and I want you to know what happened here, put the little dot for times. Don't use an x for times. That's horribly confusing with an x value there. But that's condensed. We've made it to one logarithm with just an argument that's maybe more complicated. If you look at part B, what's happening to these two logarithms? So that changes to what? Division. So this is log base 3 of, using parentheses, 5 over z. Divide, subtract, go together. Now that's too easy. What if I give you 3 things happening at a time? What's happening for both operations? Subtraction. So what I want you to think is not that it goes into a denominator of a denominator, because that gets weird. Anything that is subtracted just goes in a regular denominator. So what I mean by that is this should be log base 10, which yes, we know is a common logarithm, but because our notes wrote the 10, we're going to keep it like that, of x on top since it's positive, then both 5 and z in the denominator because they were negative. Do we see that? So it's tempting to just, if we were to expand this, just to expand it to x and then minus 5z with the two logarithms, but you can actually separate the 5z a little more and subtract them both. Easy peasy? Cool. Let's make it a little bit more complicated. For this one, there are 2 things happening, 2 rules we're going to need to use. I said 2 rules, but I only see one operation. What's the other rule? The PM one, right? The power to a power is multiply. Because I have a number multiplied in front of this logarithm, the first thing I'm going to do is deal with that power. So I'm going to move it up here. So this should actually say log base 2 of x to the third power, we'll put that in parentheses, minus log base 2 of y. Bloop, we put it back up to the top of the argument. That makes sense? Then we can deal with the fact that this is subtracted. So now we'll deal with this. Subtract means divide. So this is log base 2 of x to the third divided by y. Yes, sir?
Will it always be the same log number?
For the little base?
Yeah.
It should be. You actually can't use these rules if those logs have different bases. Just the same way like exponents that have to have the same base to do the exponent rules, logarithms have to have the same base to do the logarithm rules. Okay? E is for you. I want you to try this one. You got it. Okay, I gave you a first step here on the board. Did we all get here? Okay, and now I'm sure you're like, wait a second. Do I divide or do I add or what? Do I divide or do I multiply? Those are great questions. So what I want you to think about is, again, anything that's subtracted will go into the denominator. Anything that's added will go into the numerator. So positive things go in the numerator, negative things go in the denominator. Which means this should end up being log base 7 of, with a big divide, the positive things, which was 4 and a squared, and the negative things in the bottom, b to the 5th. Now you might be thinking, wait a second, those are in a different order than is written. Could I write a squared times 4? You could, but people don't write it like that. You always put the number in front of a letter, a big coefficient like that. B is on the bottom because this logarithm itself is negative. And when you're subtracting a logarithm, the rule, like at the top of the page, says that it goes into the denominator. Correct. All right, letter F is a bit of a doozy. She looks really simple, but it is not. Here's the thing. Right now, your spidey senses were probably telling you, adding, that means we're going to multiply these. But remember, these rules only work if those logarithms have the same base. Is this even a logarithm? No. Weird. All right, so we need to create it to be a logarithm. Interesting. How do we do that? What we need to remember is a rule we learned about Friday before Thanksgiving break, which means we might have forgotten about it. It says that if you have, here's two versions to write it. If you have an exponent raised to a logarithm with the same base, what does that equal to? X. In the same way, if you have a logarithm with a base of a, with an argument of a, what does that equal? X. So basically I'm saying, if you have a logarithm with a base and an evaluated number that is the same, it would cancel each other out. This is going to be like multiplying by a fraction 5 over 5. We're multiplying by 1 here because it would cancel out. I'm going to rewrite f in this way. I'm going to say it's still 2, but I'm going to multiply it by that rule, giving it the same base as the other one and the same evaluated number, so it's like I'm multiplying by 1. Okay, pause. I have done nothing to this equation except multiply it by 1. Now that it's written like this, what can you do with this? Power it, yeah. That's a number multiplied in front, so now it can become a power of this 6. That would make this log base 6 of 6 squared plus log base 6 of x. Now our spidey senses can go off because we see that this has a plus sign. What are we going to do with the 6 squared and the x? Multiply them inside one argument. So this is going to be 6 squared times, give it a little times, x. Again, we don't write this little time symbol, but because these are our notes, I need us to know where things went. We'll put it for right now. We can simplify this one, though, because it's just begging to be simplified. What is 6 squared? 36. So we can actually write this as log base 6 of 36x. Now, from the start, if you didn't remember that rule that I've written in purple, there's actually no way to simplify that the way it's written on your paper. Because they don't have a same base, we'd be stuck. So we have to figure out how to make them have the same base so we can manipulate it. Without further ado, let's see if you guys can answer example 4. What? 3. What? 2. Oh my gosh. My words. I'm speaking like it's a Monday and it's a whole Thursday. So you guys have example 2. I want to see what you do with this kind of example, the way an AP test would write it. All right, let's chat about example 2. I think we've had enough time. Here's what I see. This time we're expanding instead of condensing. So my spidey senses said, well, here's a divide. So let me go ahead and just separate them by subtraction. So this is log base 3 of x squared minus log base 3 of y. But then my spidey senses were like, wait a second. There is also this little exponent floating up here. And what can I do with any exponents? Move it to the front to multiply. So the final answer would look like this. This would be 2 times log base 3 of x minus log base 3 of y, which means the correct answer was C. How did we do on that one? Fabulous. On to the back we go. Oops, get that later. Now we're going to bring in the idea of these different kind of dilations, changing them from horizontal transformations to vertical transformations and vice versa. This question says the function f of x equal to log of 6x is a horizontal dilation of the function g of x equal to log of x. Show that f can also be written as a vertical translation of g, with f of x being equal to g of x plus k, where k is a constant. Whoa, lots of words here. Let's look at some key words. We know that from the beginning, this is a horizontal dilation because of this right here. That 6x inside right now is a horizontal dilation by 1/6. Yes? Do we remember those words from transformation lessons? Okay. We are saying that it is some transformation of this basic version of the function, regular log of x. We need to figure out what we have done to log of x to create this horizontal dilation. But I want you to figure it out as if it was a vertical translation instead of a horizontal dilation. So here's what we would do. We take the function f of x. We'd say f of x equal to log of 6x. But I'm going to write the time symbol in between it so that we can remember what we can do with this logarithm. Okay, what can I do when two things are multiplied inside of parentheses? Multiply means add, heard it, which means I can change that multiply sign into an add sign as long as I give the log with the base 10 to both things. Do we see that? This should look familiar. In this problem, log of x is our g function. So if I rewrite that as g, this is going to say, okay, log of 6 plus g of x. Again, if you're like, where'd that come from? Right here. So the question is basically saying to write it as a vertical translation. We are technically done. If you notice, we have g of x, and we are adding some value to it. There is no variable in this logarithm. This is just a plain number. In fact, it is 0.778. That's just a regular number. If you were to type log of 6 in your calculator, you'd get 0.778. So we can say that this would create the vertical translation as long as the k would be equal to log of 6, which again, if you're curious, is approximately 0.778. So we would have taken the regular logarithmic function and moved it up 0.778 units. That's the same as a horizontal dilation by 6. So we used the properties of logarithms and then attached our idea of transformations to it. Since this right here is a plain constant, we are able to do that. Now this change of base property that you have here is actually pretty important. Before the advent of nice calculators, and in fact the calculators that I went all through school with, high school and college, there was not log base on old calculators. Remember how when we evaluated functions a while ago, you found that log base function in here to be able to type it in? You know what I'm talking about? Okay, before that happened, because like my calculator that I own for myself doesn't have that function, and those of you who are using the calculators where somehow it's marked out, your calculator does not have that function. We would have had to use this change of base formula since forever. So this is actually really useful, especially if you end up with a calculator that the log base doesn't work. A lot of calculators don't have this function. What the change of base property tells me is that if I need to evaluate log base b of x, whatever those numbers end up being, I can just separate it the following way. Log base a of x over log base a of b. Notice that I've just taken the base and the evaluated number and put them on a top and a bottom. You see that? Do you also see that these new logarithms have the same base? For a calculator, most calculators figure out or use the common logarithm. So this would be just regular log, wrong color, log of x over log of b, or your natural log of x over natural log of b. In a calculator, those are your options. So again, if you end up with a calculator that doesn't have log base and you're trying to evaluate, this is the formula that you're using to do that. But what's really cool about this property is it actually tells me about more transformations that are occurring for a function. It illustrates that all logarithmic functions are just vertical dilations of each other, which is wild. Now, why is this the case? That's a great question. I'm so glad you asked. If we zoom back in on the formula itself, you only have a variable up here, which means you only have a function essentially at the top. This denominator is just some constant. It's just a number. Both a and b are numbers that you're going to have chose, which means that now we have written a regular variable logarithm divided by some regular number. That is a vertical dilation. Multiplying by a number in front of a function is a vertical dilation. That's exactly what we're doing here. So let me show you an example where this works, because it's kind of confusing just to see it without an example. In example 4, it says let f of x be log base 4 of x and g of x be log base 9 of x. Show that f is a vertical dilation of g by finding the value of k such that f of x equal to k times g of x. It is asking you to find the vertical dilation number, the number we are multiplying in front of the function, which means we need to write these two functions as vertical dilations of each other. Here's what we would do. We'll take the f of x function, which is log base 4 of x. And we're going to write it using the change of base formula. But I'm going to specifically choose... Oh no, air server went away. 1 second. Okay, it's back up. Don't know how that happened. Just straight up quit on me. So we're going to use the change of base formula, but we're going to specifically choose the base we're going to use that to make it relate to g of x. What I mean by that is, what is the base of g of x? 9. We're going to use 9 as the base in our change of base formula, meaning we're going to have log base 9 of x divided by log base 9 of 4. That's the change of base formula. So I took the x value and put it on top. I took the base value, put it on bottom, with the same base for both of these logarithms. Now, I chose the a value to be 9 so that I could relate f to g. Now that I've done that, this top thing should look really familiar. In our problem, this is g of x. Log base 9 of x, log base 9 of x. So I can rewrite the top as just plain g of x. Do we follow? Okay. Now right now it doesn't really look like I'm multiplying g of x by a constant until I use some fraction rules to split this apart. Something in a denominator is the same as 1 over that something. So this is 1 over log base 9 of 4 multiplied by g of x. Now I can see my vertical dilation. Just like in example 3 where we said k is the stuff without variables, in this problem we also say k is going to be the stuff without variables. 1 over log base 9 of 4. That is what I'm multiplying the g of x function by to create f of x. So you have to get them to relate to each other the same way we did in example 3. This one just utilizes the change of base formula to make that happen. Our last example here just talks about the natural log function, which we've discussed before in this class. It kind of relates to more of the things that are on the front of these notes. So let's review and make sure we still remember the rules. We'll do this one together. If we're looking at this and we want to write an equivalent expression, we just want to use the properties. My spidey senses are telling me to look at these two numbers. What should I do with those two numbers? Power rule, making them up to be a power. So this would be natural log of x raised to the third power minus natural log of y raised to the fourth power. Now, a little bonus question here. Why am I allowed to use these properties? I don't see a base written to verify that they have the same base. How do we know we can use the properties for this natural log? Huh? Well, it is an L, not an I, but yes. What is the base of a natural log? E. So these do actually have the same base. We just write it in a natural log format. Now that it's written like this, our spidey senses should be telling us to do something with this minus. What do we do with minuses? Divide. So we should have natural log of x cubed divided by x to the fourth, which means answer choice A is the correct answer. How do we feel? Okay. Cool, cool, cool.